Hello, good evening. Today is October 21st, 11 o'clock in the evening, and I'm recording this presentation. It is a backup presentation, sort of a placeholder presentation for a keynote address I will be giving on October 26th. And the conference is IC3K, and it's a conference on information sharing, knowledge management, and it's going to be virtual, but the site of the conference would have been Lisbon in Portugal. I'm really sad that I'm not able to be in Lisbon to give this keynote presentation. Nevertheless, I'm happy that I'm able to give this presentation virtually thanks to technology. And so I will be giving this presentation live on October 26th. I think it's going to be at 11 o'clock Dallas, Texas, US Central Daylight Time, which is going to be 5:30, actually 5 o'clock, I believe, in the evening, Lisbon time. And so I'm really looking forward to giving this presentation. And so I'm going to share my screen. By the way, it's October 21st, 2021. Okay, so I'm going to share my screen now. And by the way, I'm Bhavani Thuraisingham from the University of Texas at Dallas. So the title of my talk, just a second. Right, the title of my talk is Integrating Big Data, Data Science, and Cybersecurity with Applications in Cloud and Internet of Things. So I use the word data science synonymously with machine learning, artificial intelligence. And so how do we integrate the two, data science and cybersecurity? And the applications I'm focusing on is the cloud and the Internet of Things. Okay, so my talk will be in 4 parts. Part 1 is integrating cybersecurity and AI/data science. And so there I will be discussing multiple topics: big data security and privacy, privacy-aware quantified self, data science, machine learning for cybersecurity applications. And one of the hottest topics right now in machine learning, AI, is what happens if these machine learning techniques are attacked. So that's securing data science, machine learning, AI, and then trustworthy machine learning and AI. So part 2 is going to be security and privacy for Internet of Things. And in particular, I'll talk about Internet of Transportation and infrastructures. Part 3 is applying part 1 to part 2. So applications of SecAI, by that I mean security and AI, for smart world systems, Internet of Transportation and infrastructures. And part 4 is the role of the cloud. And I'd like to acknowledge a number of our sponsors: National Science Foundation, Army, Air Force, Navy, and NIST and NSA, and my colleagues, Professor Alvaro Cardenas, Murad Kantajalu, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan, our former PhD student, Dr. Raul Quenenas, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1, SecAI, integrating cybersecurity and AI with data science, machine learning. So I'm going to give a bit of a motivation: data mining, security, and privacy. So I introduced this idea, I believe, data mining, security, and privacy, at a keynote address I gave at the IFIP 1996 conference in data and application security and privacy. That was in Como, Italy. That's over 25 years ago. And later, Pacific Asia Knowledge Discovery Conference in 1998 in Melbourne, Australia, and subsequently published a landmark paper while I was a program director at NSF in 2002 that spawned a new area of research. Why do I call it landmark? I'm just, not that I want to brag, but it's just that when you are a program director at NSF, and then when you publish a paper, sort of providing directions, then of course everyone pays attention and that paper gets a lot of citations. Okay, so later on, a couple of years later, the privacy-preserving data mining term was coined by researchers at IBM Almaden, Dr. Rakesh Agarwal and his colleagues, And so what they said was, okay, you don't want to give out the sensitive information, such as the disease you have and so on. So you have the original data, right? You add a little bit of noise, right? And X prime is the noise added data. And then you have a modified data mining process. The noise could be randomization, or you can perturb the data a little bit. So if you're 25 years, you can say 26. It doesn't make a big difference, but you don't want to say that you are 55, right? That's a big difference. So the final modified data mining result should be the same. Otherwise, what's the point in doing data mining? So I joined the University of Texas at Dallas in October 2004. And together with my colleague, Dr. Murad Kantajalu, we supervised a student, Dr. Lee Liu. She was my first PhD student, and I believe Dr. Kantajalu's first PhD student at UT Dallas. And Dr. Lee Liu, she focused on privacy-preserving decision trees, and in particular, the perturbation method between 2005 and 2008. So today, right, with big data and so on, data mining, security, and privacy is exacerbated because of big data and data science. So I hosted the NSF workshop on big data security and privacy in September 2014 and presented the results to the interagency working group in February 2015. Okay, so that was a big milestone, I would say, because I believe that's the first time, people were talking about big data security and privacy. Okay, so what do we mean by big data security and privacy? So due to the technological advances and novel applications, it is now possible to capture, process, analyze large amounts of data for security tasks and even other tasks, right? Whether it's be healthcare, or whether it be financial applications or manufacturing, or even cybersecurity, like insider threat detection and intrusion detection, malware analysis. We are using lots of data being collected. And these tasks also include user authentication, access control, anomaly detection, and so on. So by collecting lots of data, plus additional data on the web, you can put it all together. But of course, it's very useful because it can help with homeland protection, disease outbreaks, and so on. But the collected data, even if anonymized, that means you have two records and you remove the identifiers. And when you put all these records together, when you link them, it may re-identify the individuals. Okay, so when you link this anonymized records, then you can re-identify the individual. So that's the danger. Security tasks such as authentication and access control could require detailed information about users. Multi-factor authentication, you need to have face recognition, so facial features and fingerprints and voice. And so when you put it all together, imagine somebody could masquerade as you. So that's the danger. This information, if misused or stolen, can lead to privacy breaches. So what are the challenges? Securing the data, access control models, privacy enhanced techniques, big data analytics for cybersecurity. And of course, I said the hottest topic, what happens if these machine learning techniques are attacked, right? Because we are using machine learning for a number of applications, whether it be healthcare or finance or even cybersecurity. So if these machine learning techniques are attacked, it could be a complete disaster. Okay. So now I'm going to talk about some of the work that we've done. One is privacy-aware quantified self. So many mobile devices, smartphones, it's become prevalent. And of course, we've got glucose monitoring, blood pressure measuring gadgets and Fitbits, so much of data being collected. And so there's a recent movement called quantified self that sociologists and psychologists are focusing on, that is collecting lots of data and analyzing the data and giving advice to the individuals. So for instance, I really like vanilla ice cream and milk chocolates. So wouldn't it be great when I open the refrigerator, right? Of course, I don't want to keep any milk chocolates and vanilla ice cream in the refrigerator because it's too tempting. But suppose I have, and I go and grab a piece of chocolate. Wouldn't it be great if there's a message immediately sent to my smartphone, or maybe even a voice speaking from the refrigerator saying, oh, you should not be eating milk chocolates. But imagine what that means, right? That means so much of information would have been collected, and the fact that I like milk chocolates, or maybe what happens if it's smoking, right? Maybe I'm a secret smoker. And so that result could be sent to my insurance company. So that could be a disaster. Okay, so what happens? Why this quantified cell movement is really great with respect to improving health habits and so on. But there's also a big problem because privacy could be violated, right? So such data collection and sharing usually often being carried out without the user's knowledge, right? So that brings grave danger because data collected, a device monitoring blood glucose levels might be used by the insurance company, not just to deny insurance coverage to me, but also my son and my grandchildren. And so that could be quite concerning and devastating. So such privacy violations could easily get out of control if data collectors could aggregate financial and health-related data with tweets, Facebook activity, purchase patterns, and so on. This could result in lawsuits. So to address these challenges, we really need tools, not only for quantified self, of course, to help us, but privacy-aware quantified self. And those are the tools that we are developing. So this is our framework. So policy-based, privacy-aware data management framework. What we are saying is data is being collected, health information, fitness data, location data, social media, image, video, all kinds of sources. And it's being collected just in our smartphone, right? Data collection, data storage and access, data analytics, data sharing. And then you have this cloud storage, right? Encrypted backup data that's stored in the cloud. And then you have through this, of course, data is stored in the cloud, and then some cloud-based services, right? Some anonymized encrypted data sharing and query results, right? You query through these services, go to the storage and give you the results. So that's the whole idea. But what we are stressing here, every step of the way, collection, storage, access, analytics, sharing, they have to be governed by policies, appropriate policies. These are not TOY policies. We are working with policy experts, right, to develop these data sharing policies and data collection, data storage, and so on. Okay, so this is sort of our approach. So this is our smartphone and the cloud-based storage. So more data being collected. I'm just sort of repeating here what I said earlier. Will not be sufficient to store all of the data. So some data in your smartphone, local data, and lots of the data in the cloud or an edge. Based on the access control policies, local apps running on the device will be granted some access, and some access can be granted to the backend storage in the cloud. So you may not have to collect too much data, right? For a 20-year-old, do you want to weigh the 20-year-old every day? Because let's say the 20-year-old eats a lot and puts on weight, say 3 pounds for the next day. It may not be so bad, a reasonably healthy 20-year-old. But if you're 70 and you put on 3 pounds, that could be dangerous because that could sort of tax your heart, right? Your heart may not be as strong as the heart of a 20-year-old. So in other cases, data, this is the challenge. Data may have to be deleted to preserve privacy, right? Delete and or generate fake location data to hide the fact that person participated in a protest. So when data is deleted, it's not like you go to the bank and you put your jewelry in your safety deposit box, and then you can remove your jewelry and there are no traces, right? Even if a duplicate is made, if your diamond jewelry, nobody is going to duplicate it with the other diamonds, right? They might do some fake jewelry. But in any case, you can even test to see whether they have put some fake jewelry in there, right? So there's only one piece of physical object. But then for data, when you delete it, who knows? There could be copies all over the place. And so that's why you need delete policies, which have to be accompanied with, say, audit policies for accounting purposes, that the data, in fact, has been deleted. So we envision the data sharing analytics will be carried out using services, which I showed earlier the picture. And based on the different scenarios, some data could be encrypted, some data may be sanitized, some data modified, right? So different sort of perturbation methods and sanitization methods for depending on the data. So that's our privacy-aware policy-based. Again, policies have to guide, right? Data collection, storage, access, analytics, learning, sharing. Okay. Next, we go on to the next topic. So we finished we finished a big data security privacy, privacy aware data management framework, now data science for cybersecurity. So usually what we have been doing for about 20, 25 years now, you build past data to build a classification model, such as is it good or bad class, or is it pink, red, blue, yellow class. You predict the labels of future instances using the model. So based on what you have learned, right, you predict the future labels. Is it a red class or a blue class? And that helps in decision making. So you can ask, okay, so what's the challenge? I'll tell you. So we have all this network traffic coming, and we build a classification model. And so we do the test training. And then when the test case comes, if it's attacked, we block and quarantine, otherwise benign traffic. So this is what we have been doing. But the challenge is this big data stream. Continuously, data is coming, lots and lots and lots of data. Network traffic, later on we'll see sensor data. And so the concepts are going to change. Suppose that you're going to use it for financial, stock market prediction, right? So today it will say by Microsoft, tomorrow it's by Facebook, the next day by Apple, then by Amazon, then by Facebook, whatever, right? So concepts are changing. That means the models will have to be changed as the data is changing. So we build an ensemble of models, right? And then some of the outdated models or bad models, we will throw them away. So we have an automated algorithm that we have developed for building an ensemble of models. There could be a human in the loop just to make sure. So these models are continuously being updated and the outdated models thrown away. So big data streams, continuous flow of data, very common in our connected digital world, and massive amounts of data. So ensemble of models that can rapidly change, because back like 20 years ago, we didn't know how to do real-time data mining, right? Because we said data mining, you build classification model. And so we said there's no such thing as real-time data mining. But today, with this ensemble and update classification, creating an ensemble of models, we could do real-time data mining. So that's the data science for cybersecurity, but I'm going to talk a little bit more. We applied it to insider threat as well as some other applications. What's insider threat? Bad people pretending to be good people in an organization. These are the people who carry out espionage and do so many bad things against the country. And so but they have all the clearances, they pretend to be really good people. Similarly, there are bad processes, malicious processes, but you may not detect. I mean, just like a good process, right? So that's what we've got to find. So it's a big challenge. So we've designed and developed ensemble-based, our stream mining or stream analytics, stream data science algorithms or stream-based machine learning, supervised learning that address the challenge by maintaining evolving collection of multiple models, ensemble of models to classify dynamic data streams of unbounded length. The result is a classifier that exhibits substantially increased classification accuracy for real-time, real insider threat streams. So traditional support vector machine and one-class support vector machine. We also designed and developed unsupervised algorithms, right? Supervised, again, you learn from all the labels and so on, and then you predict the labels for new data. But unsupervised, you have no way to know. So you have a group of staff, you sort of look at it, the algorithm, and then see some patterns. Oh, this goes into one class. Okay, these are the classes where these people look like they prefer vanilla ice cream. These people, it looks like they prefer chocolate ice cream and so on. So that's unsupervised. And we used a graph-based anomaly detection as well as complex dictionary, number of unsupervised algorithms, unsupervised learning, compression-based techniques to model common behavior sequences. The results, the classifier, it did substantially better performance and accuracy than the supervised algorithms. Okay, so I'm going to show you our architecture. So this is our architecture. So what happens? The people are sort of typing away all these system calls and so on. You take the I chunks, and then as a new chunk comes in, you extract the features, and then you apply these learning algorithms, support vector machine, GBAD, and so on, graph-based anomaly detection, ensemble-based stream analytics, and you build the ensemble model. So you may build a new model, or you may say the old models are still fine. So as the new data comes in, we are continuing to build models. Now the I+1 chunk comes in, extract features, and then you test using these models. And then it can say, is it an anomaly or not? But you don't maybe have to use, say, the model that was developed day before yesterday could have been outdated. So you've got a new model that you might have developed maybe an hour ago, which is still valid, right? So that's the whole idea. And I'm also referring to a number of our early papers on this topic, okay? Okay, so now we come to securing data. So we have applied data science for cybersecurity, right? Similarly, data science can be used to develop drugs, therapeutics for COVID-19, healthcare, try to figure out people who live in this part of the country has got, certain kind of diseases and so on, or financial applications, manufacturing. So you can use data science for a number of applications, including cybersecurity. But what happens if the machine learning data science techniques are attacked? Then you cannot rely, right? The system can tell you that you've got just a mild cold, but you could be really having COVID, right? If the testing is bad, right? COVID testing, it can say you could really be having COVID and you are just treating it for a cold, and very suddenly you can change, within a matter of hours, you could get very, very sick. Okay, so that's the disaster, right? So the data science models can, if it's attacked, it can say, it can tell the patient has got something and then give some treatment, and then the patient could die. So it's really life or death matter. So how can it get attacked? The adversary modifies data to defeat the learning algorithms. Adversary can either modify our model, thwart our model, or adversary can corrupt our data so our model is invalid. Okay, so it's adversary. So understanding adversarial learning. Adversary is learning. It's not concept drift. It's not online learning. Adversary adapts to avoid being detected during training time, data poisoning during test time, modifying features when data mining is deployed. So there's a game that is played. A game is played between these adversary and you, right? So it could be Stackelberg game, it could be zero-sum game. So game theorists are working on it together with computer scientists and cybersecurity machine learning specialists. So let's see what happens. Support vector machine, this is the boundary line. All the red instances are bad instances and the blue instances are good instances. Adversary is watching, right? Learning what we are doing, our data and so on. And then it knows exactly how we are classifying, learning our model. So it's going to try and push the bad instances down here, see, and now these 1, 2, 3, 4, 5 red instances, which are bad, we will think that they are good. That means we have now false negatives, which is very bad. We don't want false positives. We don't want false negatives. So what do we do about it? What we do about it, before we do anything, we need to understand what the attack models. There could be any type, number of attacks. Remember, all the adversary has to do is to find one loophole. We've got to cover everything, and that's almost impossible, right? So we've got to do the best we can. So we've identified 2 classes of attacks: free range attacks, where the adversary can move the malicious data anywhere in the domain. Our paper, I'll show you the paper. We have cited our paper. It's one of the early papers on this adversarial support vector machine. And then we have a targeted model where adversary can move malicious data, closer to a target point. Okay, so look what happens. So what we do is, this is the original support vector machine. Black dashed line is a standard support vector machine classification boundary. And the blue line is the adversarial support vector machine classification boundary. So what we are trying to do, applying all the games, before that, the red crosses are bad instances. The green circles are good instances. What we are trying to do is move, right, this original support vector machine somewhere here to the blue line, right? That means some of these crosses, right, 1, 2, 3, 4, like 6 or 7 crosses will be detected. Earlier, it would not have been detected because it would have gone into the green circles, and so it would have not been detected. But now we are detecting some of the red crosses. Okay, of course, we are also getting some false positives because of that, right? Because look, these green circles are showing as false positives, but at least we would have caught some of the bad instances. Of course, you could ask the question, why not move this blue line right here? But imagine if we move this right here, all of this would be shown as bad instances. So we are going to have lots of false positives. So that's where we have to draw a balance, right? Because without a doubt, we are going to get false positives and false negatives. The whole idea is to reduce these false negatives. So if they are really bad, we want to show that it's bad, but we don't want to move it too far. And the same thing that we are talking here, it's more visually displayed. Again, green circles are good, red crosses are bad, and all these black points here are the ones that these are bad ones, but it's showing that a lot of the black are being caught as bad, but some black stars have gone in here, which will not be caught, and some green have come here. So we are going to have some false positives as well, but a lot of the what would have shown as false negatives had we had the line here, they are now being caught, right, as actual positive. So we have 4 things: positive, negative, false positive, false negative, just like for COVID-19, right? You can have a positive test or a negative test or a false positive or a false negative test. Okay, in many ways, the viruses, right, are very similar to the malicious code. Okay, so now this finishes adversarial machine learning, right? And you can see our paper published in KDD. It's one of the, it is the top data science conference. Okay, so we are also, I'm going to just look at the time, started, I believe, sorry, yes. So what happened? Okay, so that's good, we are okay. So the other question is, what about trustworthy machine learning AI analytics, right? So what do we mean by that? Computations are being carried out, massive amounts of computational resources and third-party services to outsource some computations. When third-party survey is used, of course, it's corrupted, right? Because we don't know who the third party is. So you can have man-in-the-middle attacks and so on, right? Or insider threat. So what are we doing? There are 2 things we can do. One, we are conducting research in using the Intel's platform, SGX platform, for secure encrypted stream data processing. And I'll show you in a minute, right, to support the trusted execution environment. We want the execution to be trusted. Another area that is really, that's showing a lot of promise, and that's formal methods, right, using logics and coming up with formal methods techniques for machine learning algorithms, and making sure that the algorithms, right, the implementation meets the specification. Of course, we know that formal methods, it's very expensive, but in many cases it has shown to work. So now with all the latest technologies, you know, we should, I mean, it's sort of, it comes and goes, just like AI, right? There was a lot of interest in AI in the 70s and went down in the 80s, 90s, but now AI is everywhere because technology has improved. And similarly, you know, there is formal methods is showing promise. Okay, so this is the Intel SGX platform where we have, you know, this is the Intel application, SGX libraries and wrappers and encrypted code. But the main point is our data analytics algorithm is being executed in protected domains, right? SGX enclave memory, and it's executed in protected domains to provide security. So I'm just going to, there's a lot more details and we have written a number of papers here, but that's all I'm going to say. Okay, so that finishes part 1. Part 2, right, we have got 4 parts. So I'm going to take sort of 10 minutes for each of the parts. So part 2, security and privacy for Internet of Transportation and critical infrastructures. Okay, so we have Internet of Things, right? Our telephones are connected to our coffee makers, connected to our television, to our refrigerator, to the alarm clocks and our buying and our cell phones. Everything is connected, right? That's Internet of Home Things, maybe, right? Home things or house things. But similarly, transportation, cars are connected to trains, connected to trucks, and connected to so it's connected to the roadworks, right? So they're all connected. So that's Internet of Transportation. Internet of Things has major implications in the transportation industry. Autonomous vehicles aim at improving day-to-day activities, delivering packages, improving trucks, and so on. US alone, right? In US, trucks alone carry estimated 63.3% of freight of goods, right? So this whole thing is about autonomous vehicles. It's a big thing now. AVs are not limited to ground vehicles, but also include aerial and sea vehicles with a wide range of applications. Levels of automation for AVs are from 0 to 5. with current ground vehicles in the market have got partial automation about level 2, and aerial vehicles have got automation is better of level 4. Companies are spending a lot. GM spent 728 million in 2018, a billion in 2019, and very likely more in 20 and beyond. So we need to get the numbers for 2020. While there's great potential in AVs, what's the big challenge? Security and privacy, right? We love for the things to work exactly as they are supposed to work, but if they are attacked, you can have so many crashes, it could be devastating. The security, and I showed you privacy is also important. So security of autonomous vehicles. AVs evaluate their environment using a variety of sensors, camera, GPS, inertial measurement units, LIDAR, radar, and so on. Prior research has shown that sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS are susceptible to spoofing signals. Vehicles should verify the veracity of sensor signals before acting upon them. Okay, so for instance, with sensor-based, right, AVs rely on sensors to evaluate and interact with their environment, okay? And sensors are susceptible to GPS spoofing and transduction attacks that manipulate environment physical signals, visual, magnetic, and so on. Classification computing, such as memory protection, cryptography, and so on. So inherited issues are this, right? The types of attacks, needed defenses. So okay, so the traditional memory protection and so on, yes, we need them, but we need a lot more, right? Because the environment, these are tiny devices. So, and also it's hard to verify due to real-time constraints. AVs trust and act upon sensor data without any form of verification, okay? So I just want to make sure everything's fine. Okay, so what did we do? We built a physics-based anomaly detector to build a reference monitor. That's the security critical component using physics. Right, so I'm going to explain our algorithm. You might say, so what's the big deal? The algorithm consists of 3 parts. Build a model offline using the physics-based, the autonomous vehicles physical invariants. Then implement an online tool to monitor expected and observed behavior. Raise an alarm if significant residual differences exist, right, between executions. Pre-processing offline, online verification, anomaly detection. So what's the big deal? This is what we do all the time. There are many challenges. Challenge is to get this thing, the model, right? Getting all the properties, identifying all types of attacks, right? So look at this model here. K is a state, input sensor measurements, all these parameters, LX, LY, LZ, moments of inertia, M is the mass of vehicles, and you need to get, and this is something computer scientists, we are not as trained to do this. So that's why Dr. Cardenas, my colleague, he's a top expert in control systems. So he was developing the model. And so offline pre-processing AVs invariants are calculated using a well-known nonlinear models for aerial and ground vehicles, accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis, right? So accelerometer, gyroscope, and magnetometer is used for the aerial vehicle. Vehicle position and steering angle is used for the ground vehicle. So online stage, we could have used some fancy machine learning. That's what we are looking at now. But at that time, we said, okay, extended Kalman filter. That's been around for a long time. Control engineers have been used, electrical engineers, control systems engineers have been using Kalman filters to predict AV's physical behavior by estimating unknown parameters by noisy sensor input. The algorithm is divided into 2 sections that predict and corrects the estimation before it is compared against the sensor data. Anomaly detection, we use the Kusum algorithm. It's a statistical based algorithm, is then used to detect persistent attacks. An alarm is raised if the residue difference is larger than a predefined threshold. Okay, so what's the challenge, right? So Kalman filter and so on, it's been around, but the challenge is to model and identify the various aspects of this model that can be attacked. So we need to study the types of models because these are very complex cyber physical systems. It's not like a sort of a computer system or a laptop or whatever, right? A computer system or a network system. These are complex systems. Okay, so the physical implementation, we have aerial AV. We did it, as I said earlier, we experimented with drones and cars. land vehicles and aerial vehicles. So aerial controller PX4 flight controller used drones focused on detecting GPS spoofing and gyroscope attacks. GPS attacks detected in 0.2 seconds. Gyroscope attacks are detected in 1.5 seconds. Okay. Overhead introduced is around 5.4%. Ground AV custom built on top of Traxxas Ford Fiesta. Controller is ROS kinetic aim and focused on detecting visual attacks on the camera. Attacks detected after 0.1 seconds. Overhead introduced 2.25%. Each threshold produces a probability of false alarms of approximately 2%. Okay. So we didn't experiment with sea vehicles because, you know, maybe we could have had gone to a small lake or something, but we only did for drones and cars. Okay, so that's our security. Now, privacy. Beyond the security of vehicles, right, the transportation sector could greatly benefit from a supporting infrastructure that allows communication. So we really want communication between all these vehicles, right? Lampposts and surveillance cameras and sensors on lampposts and traffic. What we really want these systems to tell us, right? Where is the congestion? Avoid these routes. Oh, you're going too fast, and avoid collisions and crashes and all of that, right? So this is really, really useful, and bring in machine learning. It's just absolutely, you need it. However, from a user's perspective, getting all this data, I might want to smoke in my car, right? Or I might want to be in a certain location. I don't want anyone else to know where I am. And so, or I'm an erratic driver, right? So privacy concerns arise from all the information that's being collected. And, you know, my driving pattern, somebody could take that information video and send it to my insurance company, car insurance. So that's why legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent. This will aid at improving public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies, right? So again, people are concerned, just like the COVID-19, right? People are concerned because they think going and, at least some of them, going and taking the vaccines could really do them harm, and getting COVID-19 might be better. But that's why they have to explain, right? The healthcare professionals and so on have to explain how useful it is to get the vaccine, right? How not only useful, it's critical to get the vaccine. Similarly, right, we have to explain that, you know, so that people will use these technologies. Without a doubt, these technologies are very, very useful for them in their day-to-day lives. But if we can give them some assurance that some level of privacy is being provided, policy-aware data collection, then of course they will be more ready to use the technologies, right? So that's the whole idea. Okay, so part 3 is applying, that's our current research, applying part 1 to part 2, applications of security and AI for Internet of Transportation and infrastructures. So this is going to be fairly short, part 3, because, you know, I'm almost, let's see, about 35 minutes. So data science, AI, and transportation security. Internet of Transportation systems subject to attacks like cyber-physical systems. So streaming data is being collected, right? Remember all the sensor data that's going between trucks and cars and roadworks and trains and ships and airplanes and whatever, right? Streaming data being collected. As transportation systems go electric, you need to also conserve energy. Threats to the security of such systems could cause massive damage, right? Including accident loss, stranded on highways, and so on. So data science ML techniques are being applied to analyze the data. Can stream analytics that I mentioned earlier for our network traffic data and ensemble of models and they are also being applied to financial data and telecom data. Can we apply them for transportation data? That's a challenge. The main question for us is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensors being collected. So that's data science for transportation security. Second is adversarial machine learning, right? This is even further away for us. So Internet of Transportation will draw heavily from AI ML. Without a doubt, we need AI ML for us to be, you know, to minimize all the collisions and maximize safety and all the greatest things, you know, the routes to follow. So much of help, right? So there's also this whole area called vehicular social networks these days. Is also helping drivers. Anyway, machine learning is helping the drivers a lot. But what happens if the machine learning techniques are attacked? That could be disaster, right? There could be all kinds of collisions and crashes and so on. So adversaries attempting to thwart our learning process, the vehicle's learning process, the vehicle's model, and the vehicle's data. Therefore, the learning algorithms have to adapt to thwart the adversary. Remember, moving that line to the blue line, we have to do something similar here. Eventually, it becomes game playing between adversary and the vehicle's machine learning algorithm, right? So what sort of game between us and the vehicle and the adversary? Zero-sum, Bayesian, Stackelberg, so we have to understand the data, and research is only beginning. Then, of course, remember my smartphone with data collection, healthcare, social media data, and so on. So instead, we have a similar gadget, but inside the car for data collection, data storage, analytics, and sharing. But the data we collect, radar, GPS, cameras, LIDAR, ultrasonic sensors. And then some of the data goes into the edge or a cloud, and some data into cloud-based services. So what we are developing, privacy-aware, policy-based autonomous vehicle. Okay, that means, and we haven't done this yet. This is what we are thinking about: policy-based data collection, data storage, data analytics, data sharing. Okay, so that finishes applying part 2 to part 3. Now we talk about the role of the cloud. So massive amounts of data. So where is the cloud coming into all this? Edge and the cloud. I mean, edge is, especially with IoT systems, you need the edge, right? Because cloud could be somewhere far. And so it may take a long time for stuff to go to the cloud and back. So edge is somewhere nearby to that particular component of the IoT where you can store the data. So anyway, while massive amounts of data are collected by the IoT system, the privacy of the individuals have to be protected. As in more and more sensor data are collected, the storage on the AVs will not be sufficient, as we said. So as I said, we envision encrypted cloud storage component where all the data or less frequently accessed data pushed to the cloud. Based on the access control policies, local apps running on the AVs will be given access to some of the collected data. When needed, these AVs will be allowed to access some of the encrypted data. So AVs, autonomous vehicles, can access some of the data in the cloud. We envision much of the data sharing and analytics will be carried out using the services running on the cloud. Information sharing in the cloud is not only between AVs, so AVs can share data through a cloud. AVs can also share directly data between them, okay? So information sharing in the cloud is not only between AVs, but also organizations that are responsible for secure AVs. So data could be shared through the cloud or directly between the AVs, but through the transportation agencies, the insurance companies, maybe hospitals. So that means the cloud must be secure, because you can't run this whole thing, right? You can't expect the IoT system to be secure and the cloud not being secure. So we've done a lot of work on cloud security, layered framework for assured cloud computing, secure cloud. So we have a layered architecture, the secure virtual network monitor. So that we didn't focus on that. The pink parts still need work. The blue parts are completed. So we have a secure Zen Linux, the virtual machine monitor. That's a hypervisor. And so some of my colleagues worked on the hypervisor. Some of my other colleagues worked on securing the cloud storage infrastructure like Hadoop, MapReduce. So this was done a few years ago. So today we will be using, maybe we will also use Spark. And then we'll have Secure Hive, Sparkle Query. And this is, I was involved in this. And applications could be a number of applications: Internet of Transportation, information sharing, and so on. And our policies, we use semantic web technology. So our policies were in XML, XACML. We also use some semantic languages like RDF to express more expressive languages. And of course, some of my colleagues looked at risk and the costs involved. What is the trade-off between risk, cost, and the utility of the data, right? And then the quality of service, resource allocation, and monitoring the cloud, because the cloud also, cloud could be attacked. So we developed this, and then we developed a information sharing system in the cloud, right? So we didn't do it for transportation, but we just did it for, we have 3 organizations. We did it for the Air Force. One site was Dallas, one site was London, one site is in Subria in Italy. And so all of us, right, we put our data, pop in all our data and our policies in the cloud. And so data is shared between multiple organizations according to the policies. But one problem here, okay, so this was very good for us, right? If it's traditional cloud, store lots and lots of data, according to the policies, the data could be shared. So when we talk about autonomous, so between the agencies, agency 1, 2, and 3, transportation agencies and local agencies and federal agencies and state agencies could all share data, which is great through the cloud. But when it comes to autonomous vehicles talking to each other, that's what we need to think more. And we haven't done that yet. Is it worthwhile to share data through a cloud, right? Because data has to be shared very quickly between the autonomous vehicles. So should they share the data through the cloud, which is going to be very consuming? And that's where we may have to use some edge technology where we store the edge very local to all the nodes, or directly they should be able to share the data. Okay, but then how do these policies, what roles do these policies? Because policies have to govern data sharing. That's what I've said, right? So that is something that we need to think about. So what I'm saying is, the stuff that we did for the cloud, information sharing and securely with the policies, right? How can we apply that to an autonomous vehicle environment, Internet of Transportation? So some of the technologies that we use, we have RDF data processing, the policies are in RDF, we use MapReduce query processing. So this is really our cloud and policy, secure cloud policy processing. Okay. And so some of the directions, this is my last chart, or one before the last. Developments in integrating cybersecurity, AI, data science exploding, right? Without a doubt. Applications of AI for security, I talked about it, right? Inside a threat. And of course, the machine learning techniques could be attacked. Adversarial machine learning, I talked about it. And then I talked about development of privacy-aware healthcare and managing one's life's activities, privacy-aware quantified self. At the same time, with the development of the IoT and Internet of Transportation, security and privacy solutions, we are beginning to look at it. Right, without the machine learning, we have done quite a bit, physics-based solutions. But as driverless cars become a reality, more and more of the AVs will use AI ML techniques. So how can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work in such systems? Can we develop a privacy-aware policy-based data management framework for IoT and infrastructures? Is it possible to perform trustworthy machine learning? Can we use the Intel chip here, Intel SGX platform, right? What about formal methods? What sort of formal methods do we need? And again, I talked about the cloud, and again, my experience with the cloud, we built a secure cloud, and we have also demonstrated how our secure cloud could be used for data sharing. But how can we use this cloud for this Internet of Transportation environment? So what I'm saying is there are numerous opportunities for substantial research and development. And so what I mentioned here, right, the directions just in this chart could be enough for probably 10, very likely 10 PhD theses. Okay, so the last chart, I'd like to thank, right, my colleagues, Professors Alvaro Cardenas, Murat Kantajulu, Latifa Khan, and Dr. Former PhD student, Dr. Raul Quenenas, and of course, our project coordinator, Ms. Rhonda Walls. So I'm going to stop sharing now. And sorry about this, all these things are coming, right? So what I'm saying is, right, so this is the end of my presentation. And as I said, thank you very much for listening. And first of all, I'd like to thank the conference organizers for inviting me to give this keynote presentation. I'm truly honored. And I will be there on October 26th to give this presentation live. And hopefully I'll be there to answer your questions. And it was really good for me to give this backup presentation, because I know really where I need to cut, because I've sort of I've talked for about 50 minutes. So I know exactly where to cut and where to focus on. And so I will see you all, I guess, in about 5 days or less than 5 days. Okay. And again, thank you very much. And I'm going to stop the recording, right?